start up. So we were discussing this problem last time. What's the Poisson predictive distribution? So just as a reminder from last time, Poissons look like this. Their expectation is constrained to be their variance. It will tell you in counting models if you observe the variance being less than your expectation, I'm going to guess something's happened, like you have mixtures of Poissons. So that sort of stuff should not be derived through the exponential family. And so you reach some contradictions, but you can see in counting data, if it's a one modal distribution, over dispersed data, the variance is larger than the expectation. But for the variance to go down in a counting model, that's probably a mixture of phenomena. That's just a note to your modeling selves in the future. If you see that, you're not looking for a one component model anymore. That's my guess. And so my quick, intuitive way of explaining this is just think about counting. When you start trying to count big numbers, you start making more mistakes than when you're counting small numbers. So these are counting models. These are limits of binomials, so rare event models. You might think something like that. So rare events that occur that you're counting things, maybe it's a Poisson. Always check characteristics of your data and see if these assumptions are reasonable. I remember being in an undergraduate class and somebody gave us some data for a midterm, take-home midterm, and it was counts, and they said which distribution and find the parameter that underlies that distribution. Now the only counting model I knew about was a Poisson. It was the only one that anybody had ever given me before. And there are other ones, and I'll show you how to make an infinite collection of them in a little bit. But I looked at the column of data and I inputted it into my calculator, and the variance was like twice as big as the expectation. And I went back and I said, I don't know, because, and they're like, well, just write down Poisson, that's all I'm trying to do. And it's like, well, where did these numbers come from? And the instructor said, I made them up, and it's like, they're not Poisson. So you should have, generated them from a Poisson model. And so what were they? Well, they were made up numbers. They didn't actually come from a distribution, and that's kind of a clumsy error. So I would say, but check these sort of things and see if you agree with modeling assumptions. Of course, when you look at data, these aren't going to be equal to each other. They're going to be close to each other. So we were trying to do the Bayesian conjugate analysis. We looked at the likelihood function, and we were able to figure out the conjugate prior was gamma. And we derived the posterior distribution that I wrote like this, lambda given the data is a gamma, and these are its parameters. And I usually write this down as alpha tilde and beta tilde. These are my updated parameters. So in a conjugate analysis, all you're doing is you're updating the parameters that underlie that distribution. And so that makes it at least very nice to work with. Now, we know that the expectation of this is where we left off last time, is this parameter over that parameter. So alpha tilde over beta tilde. And that's sum of the xi's plus alpha and plus beta. A lot of times I look at the means of distribution to see, does that make sense to me? It's on the scale that I'm usually familiar with. And this looks a lot like the sample average, but it's a little bit penalized by alpha and beta here. If we picked alpha and beta to be 0, we would get back the average. And that's probably your typical estimator for estimating lambda. So under alpha equal to beta, and I would say that alpha equals to beta makes sense. Probably want that. Can anybody give me an intuitive reason why I probably want alpha and beta equal to each other? It's symmetric. And so I don't want to bias this thing all over the place. So I don't want to yank this thing all over the place. What's the mean of this thing? What am I doing to it? Think about the variance being equal to lambda. So this is acting in some way a scale parameter. And so I don't want to throw that thing all over the place. And so how do I want to scale things? Well, probably with scaling factors multiplying by 1. And so that's alpha over beta. is going to be equal to 1, because that's the prior expectation, and so we probably want that. And so, unless you had some subjective knowledge on how to pull that thing around where you thought the expectation of this thing should be, I'd probably want that. So, probably, I'd say. And if we pick it equal to 0, and this is at least appealing, because it matches at least what we know about estimating lambda through maybe a classical rationale. And so your classical estimator for that would probably be the mean. So it's the MLE of the distribution. Typical MOM estimator is also the mean, and so you might want that. Again, that's not very good argument. It's like, well, it kind of matches my classical rationale, and so it seems like there must be a better argument for this. And if you go all the way back to the 30s, when people were like kind of cranking through some of these analyses, the argument sounded just like that, where people would say, well, maybe I want to pick alpha and beta equal to 0. Somebody might jump in and say, well, that's an improper prior. What is all of this stuff? And you just did it for these heuristic reasons. And so the whole field of Bayesian statistics developed over decades, and we have better argument for why we want those. So it turns out this is the reference choice. It's also Jeffreys. So those are the things I keep saying over and over again. And so what is the prior under gamma 0, 0? It's just 1 over lambda. And so if you're thinking of this as a scale parameter, then it has that right scale form to it. And so 1 over that thing. And it also appeals to our classical rationales. So lots of good reasons, and we'll get into the math as to what is all that reference stuff and what does that Jeffreys stuff mean.
So it's transform invariant if we choose it equal to 0?
Turns out that is the Jeffreys prior. So if I pick these equal to 0, yeah, then it's transform invariant. So I gave you a property. So when I say it's Jeffreys, I'm giving you a mathematical property. We'll be studying that soon. So more to think about. So I've got a posterior model. It's easy to compute. So where we left off last time was what's the predictive distribution. And with Bayes, it's all very easy to set up the answer to this thing. I can write down an equation. So I'll write it down like this. X tilde, that's my future, given my past. And that's just the integral of our Poisson model. I'll write it down like this. Fx tilde given lambda multiplied by our posterior distribution, integrating over lambda. So I asked you guys to think about this a little bit. What distribution do you think that is? Certainly some of you ran off and checked the answer. David?
Negative binomial.
It's negative binomial. And so let me just ask you a couple questions about this distribution. And so you might not be familiar with those, and so I'll give you a 10-minute lecture on what those things are. But what do you think the expectation of this distribution should be? I'll just ask you this. What do you think the answer to this is? So the posterior predictive expectation. Take a wild guess. What's that? Yeah, so maybe the mean, but maybe that form of the mean that we wrote down before. So if I picked alpha and beta equal to 0, then probably the mean. And so I'm going to write it down like this, just to be general, probably this thing. And if you picked alpha and beta to be equal, then Yvonne's got the answer, the mean. And I wrote it down because it is true. And so it should be the mean, right? How else am I going to guess what the future looks like? Maybe the mean. But it kind of has this entanglement with what is the mean of the distribution? It's lambda. And so what am I really estimating in this whole thing? Lambda. So kind of there's a symmetry between the data and lambda. And so maybe the mean, that's a good answer. Let me ask you, what do you think the variance should be? Bigger or smaller than that penalized mean? Bigger. So because you're forecasting. And so you have more variability. And so let's just write this down. Variance of x tilde given x, probably bigger than sum of the xi's plus alpha over n plus beta. Probably bigger than that. And you'd be right. So looks like we have some work to do if we want to verify everything, show that this is negative binomial. Let's just forget about that for a second. Let's say I didn't know how to do the integral. I could sample from this distribution. So if we didn't want to do the math, we could do this. Set up the for loop, draw lambdas, and I'm going to draw those from gamma, sum of the xi's plus alpha, n plus beta. I'll just keep it general, even though I would probably plug in alpha, beta, 0. So we'll just write it all down. So that's the posterior distribution. And then I'm going to sample the future. And I'm going to sample this from a Poisson lambda t. So that thing just comes down here. And I plug it in. So I'm really drawing joint samples, but if I just focus my attention on these right here, those are the predictive draws. And so I could get these things out of here, and I could make a histogram of them. And this is my distribution for the future. And so in practice, I could crank this thing high enough so this is smooth and it's not moving all over the place. The expectations and the variances and all the moments settle down. How big is that number going to need to be? Probably not that big. So what do I mean? Like a couple thousand. You're probably safe. So how big would I make this number really big nowadays? And so we've got lots of storage. We've got lots of compute. So make it 1 million. Why not? And then I could end up quantifying characteristics of this. I could come up with an interval from here, a 95% interval. I could chop off the tails. I'd have an equitail thing. I could find the highest posterior density, find out where the mass is densest in here. I'll give you an algorithm for that later, how we actually do it. It's kind of a hard problem. I could give you the expectations. I could give you the variances. I could compute anything I wanted out of my Monte Carlo thing. Now, of course, I don't know all the analytical properties because I haven't gone and solved the integral and recognized what this distribution is. But I could operate with it. So that's kind of a nice thing. A lot of Bayesians will do this, not in this setting. They would know it's negative binomial and they would write that down. But sometimes they have really complex models. What they're doing is basically coming up with high-dimensional histogram representations of everything. And it can tell you everything about your data set and those inferences, but they can't write down the math. So always a nice backup tool to have. You've got computers, so you should use them. Okay, what if I asked you a theoretical question like this? What's expectation x tilde given x? So maybe I could work through this distribution, whatever it is, and then I could answer this question. I could do something like this, where I look at x tilde, pi x tilde, whatever this distribution is that we work out from this analysis, and then I just sum this thing. X tilde equals 0 off to infinity. That's the definition of the expectation. This would be a hard calculation to do. And so I probably would not want to do this. If you asked me to do it right now, I'd probably mess it up 5 different ways before I got it right. Figured out how to do this infinite sum. I have to refresh my memory. But how would I do this? If I asked you to do this, I would expect that you could do this in under a minute. Remember, I'll give you the hint. It's a hierarchical representation. Annie had the answer last time. She doesn't want to give it out again. Just once. Jake's bored back there. He knows the answer. Jake, help me out.
Condition on mu as well.
Yeah, exactly. Do the iterated thing. It's not mu in this case, but it's lambda. But short. So what Jake told us, just do this. X tilde given lambda in X, we condition on X. Apologies for squeezing that in there. We can work that thing out though. And so, let's just do it. So I could pull out my computer and try to work through this thing. You give me a data set and I can give you a number. You give me alphas and betas and I can give you numbers. And so, this is a little bit more appealing if you can do it analytically because you can study it. So this is expectation. What's this inner expectation? This is X tilde given lambda and X. If I give you lambda, I don't need to give you data. So this is the Poisson model right here. So this is just lambda. The expectation of X tilde given lambda is lambda. This right here is the posterior distribution that we're finding the expectation to. So notice that we are solving 2 integrals right here. So we're doing 2 integrations to do all of this. And so you're just kind of replacing this symbol right here with some operators and you know the answers to them. They do represent these expectations, or these integrals. So what's this? This is sum of the xi's plus alpha over n plus beta. And so we've at least analytically shown that this is true. We didn't have to really do the integral, we just needed to know some shortcut steps. Okay, let's see if we can't do the integral. Before we do it, it's probably nice to know where we're aiming. So when you're writing these things down, you need to know what these things are that you're striving to get. So once you start recognizing it, you're like, oh, this looks like this distribution that I know. And so if you don't know what a negative binomial is, you can probably work through the integral, but you wouldn't know anything about it. So let me tell you about negative binomials before we attempt the integral. So negative binomial distributions. So I'm going to characterize it this way. There's other ways to characterize the negative binomial, but I'm going to say it's the number of trials. I'll write down of Bernoulli's random variables until the rth success. So Bernoulli has a parameter p. So with success parameter, success probability, Q. I'm just flipping coins. And I'm looking until I see the rth head of my coin flip. And that's going to be random. And so I'm trying to quantify that. And so you might recall that a geometric distribution is the number of draws until I see the first success. And so this is the sum of our geometric distributions. Ben?
So strictly speaking, is this the number of draws before the rth success, or is the rth success included?
The rth success is included. So like, Yeah, exactly. And so there are other ways of shifting that distribution, and some people will play exactly with that, and shift this thing around, but they're all akin to the way that I've explained it here. So some people will talk about the number of failures. They'll make that random, and that starts counting at 0, because I could see all successes at first, and you never saw failures. So some people will reparameterize this. So be careful when you're reading in your books which parameterization you're using and where it indexes from. And so the number of trials until the rth success, how many trials do I have to have at minimum? R. Yeah, exactly. So this one starts counting at R instead of the number of failures, which could start counting at 0. So let's look at this. I like to draw this picture. So I like to kind of conceptualize successes and failures. And I know that this is maybe the rth success happens here. So it happens in the last bin. And so the last thing in the sequence, if I got to observe all of the Bernoulli random draws, I know that the last one is a success. And this happens with some probability. And so the probability that this is a success is key. So that's what it means to be a success. It happened with probability key. So I'm just going to come up with the total probability of this whole sequence and figure out what that distribution looks like. So this is going to be a 1 minus p or a p in all of these, depending on if I see a 0 or otherwise. How many things happen, and I'm going to give myself just a little bit more room, up until here? It's not a trick question.
N minus 1.
Yeah, this is n minus 1 things. Happen here.
And R minus 1 other more successes.
That's right. And r minus 1 are successes. How is this distributed?
So N minus 1 choose R minus 1 times R minus 1 to, well, times P to the R minus 1 times 1 minus P to the N minus 1 minus R minus 1.
What dist is that?
That's like a binomial, except N is random instead of R.
Yeah, but this right here, now I know how many things happen. Everything's fixed in here.
Yeah.
And so this is a binomial. So this is binomially distributed right here. And I know what binomials look like. So the binomial is going to look like this. N minus 1, choose R minus 1. P, the R minus 1, there's R minus 1 successes, and the rest of them are failures. And so at least the formula that we're spouting off is a binomial distribution. And so, and then I've got this last thing right here. But that happens with probability P. This is the negative binomial distribution. So this is n minus 1, r minus 1, p to the r, to the r minus 1 times p, 1 minus p, n minus r. So
just because of that last thing, it transforms from a binomial to a negative binomial?
I mean, you just have to study the process. This was always a negative binomial. So I just decompartmentalized it into 2 pieces. So I know what the probability of the last thing is. I know what the probability of all the other stuff has to be. And so they're conditionally independent of each other, so I multiply them together. That is what it is. Notice that this kernel right here looks like that of a binomial distribution, p to the r, and 1 minus p to the n minus r, what Ben was kind of establishing by saying, well, n is random here. So this is not the normalizing constant for a binomial distribution, or for a binomial distribution. So that's n choose r. This is n minus 1 choose r minus 1. Because we've kind of tied up the last thing and said what it had to be. So this is the thing that's random. We're in a binomial distribution, r is the random thing. It's different. Normalizing constant is different. So that's negative binomial distribution. Hopefully, if you ever get stuck, you can always go back to the picture. Okay, let's try the integral. So I've got two pieces. I've got the Poisson distribution, Poisson lambda, and then I've got my posterior distribution, lambda given x. I'm going to integrate over lambda. And so this looks like lambda to the x tilde over x tilde factorial e to the minus lambda. And then my posterior distribution looks like e to the minus lambda n plus beta. Myself a little bit more real. Lambda, sum of the xi's plus alpha minus 1. And I've got some normalizing constants in here as well. I'm going to write them down. So this is gamma function of my updated alpha. That's sum of the xi's plus alpha, and then I have my updated beta raised to the updated alpha right here. So you guys are trying to see the formula. It's like this: beta alpha, gamma alpha, e to the minus lambda beta, lambda to the alpha minus 1. So that's what a gamma looks like, and I'm just updating using my posteriors. This is beta plus n to the sum of the xi's plus alpha.
So why do we care about the constants?
I guess because I want you to recognize this distribution at the end of the day, so you can see exactly what it is. If you did keep track of all of your constants, you would have an exact answer. So I feel like keeping track of them so I can show this result in its entirety because you're less familiar with this distribution. So it's because I'm teaching. And so this normalizing constant is kind of the key to recognizing that this is a negative binomial and not like a binomial or something like that. So I'm just going to keep track of everything. If you feel like throwing it all around away and you can just recognize it and renormalize it, that's cool with me too. So what I can do is I can pull out stuff that doesn't have to do with lambda. And so that is here. I don't want to lose that. I couldn't lose that because this is a distribution on x tilde. And so don't get rid of that thing. I also want to pull out, I think, all of this stuff right here. So this is beta plus n, and I'm going to keep track of it all. Integral 0 to infinity. And let's just compartmentalize everything. So this is e to the minus lambda beta plus n plus 1. Here's where the plus 1 is coming from. And then we've got lambda sum of the xi's plus alpha minus 1, and there's an x tilde in here as well. So that x tilde is being added to that sum. And I know how to do that integral. It's really easy now that I've got a trick. If you know what a gamma distribution is, you know that this integrates to the inverse normalizing constant of that thing. And so, not such a hard integral. If you didn't know that and you tried to do it by parts, it would take you some time, you'd never get an answer because it involves gamma functions. It always involves some integral that you can't write down. So anytime I use a gamma function, I really am writing down integral sign. And so, but at least I can give it some notation, and maybe I know the properties of this. And so this is going to look like gamma function. I'll have to look for my updated alpha parameter. And it's right there. X tilde plus sum of the xi's plus alpha. And then I've got beta plus n plus 1 raised to that stuff in the gamma function. That's what the integral is equal to. Now I think I'm about ready to recognize this distribution. Let me get rid of this. I'm going to rewrite this like this. Gamma function x tilde plus sum of the xi's plus alpha over gamma function sum of the xi's plus alpha times x tilde factorial. And then I'm going to write everything else down just a little bit differently. Write it in 2 parts. Don't mind, I'm going to check my notes so I get it right. It looks like that. And so you might be familiar with the gamma function if alpha is an integer. I'll call that integers. 0, 1, 2, 3, 4, 5. So those sort of numbers. Then this is equivalent to sum of the xi's plus alpha minus 1 factorial. That's an integer. So if alpha is an integer, then the whole thing is an integer. And it reduces to a factorial. Same thing up here. This would be x tilde plus sum of the xi's plus alpha minus 1 factorial. So these 3 pieces right here can be reduced to a binomial coefficient. You can just write it out however you want. There's a couple different choices, but I would take this one minus 1, choose that one minus 1, and it would look just like that. So I'll write that down. X tilde plus sum of the xi's plus alpha minus 1. Choose sum of the xi's plus alpha minus 1. Binomial coefficient. And these are my success probabilities. So this is a negative binomial. And we're done with that. So not too difficult. What exactly is the physical interpretation that I've given you, at least exemplifying what a negative binomial is? I don't know. I don't think about it that way. I don't think about it as how many trials do I need before a particular success where the success probability is this thing. It doesn't really make any sense in the context of the problem. It's a little bit different. Here's how I think about this distribution. So I like to think about negative binomials like this. So scale mixture distributions. So this is what a scale mixture distribution is. So it's an integral of some distribution. I'll just call it fx. So some dist. And I'll say it has a scale parameter. This is my scale parameter. And then I mix it over some distribution. Some distribution on the scale. And I integrate over the scale. So all I'm doing is I'm taking a distribution that has a scale parameter and I'm averaging it over some weights. So I'm smearing that distribution. So a negative binomial is a form of this. So negative binomials are scale mixtures of Poissons with gammas. Or lambda is coming from a gamma. And gammas have some parameters. So that's what a negative binomial is to me. That's how I prefer to think about it. It's a scale mixture representation of Poissons. And so what are the scale mixing weights? They're gammas. That'll induce a negative binomial. If you want another distribution, some other distribution, not negative binomial, you're welcome to play with that. And so you can come up with lots of counting distributions. If you let that be a Poisson, you change this to something other than gamma, you're going to get something different from a negative binomial. You'll be able to play around with that distribution. And so we use these tools, mixtures, to kind of warp our distributional spaces. So I have some distributions, but then I can mix over them. We can do this with centers of distributions, or we could do it with scale parameters. Let me show you another one you might be familiar with. So t-distributions. So note, t-distributions are scale mixtures of some distribution with some other distribution. So it's a scale mixture of what with what?
Normal chi-squared.
Normal chi-squared. So that's true. And Annie says chi-squared. I'm going to generalize that a little bit.
Gamma?
Tessa says gamma. So I'm going to say gamma, but that's true. Those are types of chi-squareds, but we can go a little bit more general. So this is when I take the scale parameter and I mix it over with this gamma. And we've done that calculation. So we took the variance, or at least the inverse variance, and we let that be gamma. So what I'm actually mixing with this is not the variance, but the inverse variance. And so you might say with an inverse gamma right here, if I let the scale parameter be sigma squared. If I let my scale parameter be the inverse of this, the precision, then it's a gamma. So a lot of generalities to this. And so as modelers, we do this sort of stuff all the time. We say, well, I've got this distribution, this is kind of the building block. No, I'm dealing with count data, but I see this level of over-dispersion and I want to model it. And so how do I do that? I go and get some mixing distribution to mix over with. And so that's what that is. Let's see if there's anything else I can say about this. I think that's essentially it. So I'll leave it to you guys. Any questions about all of this? I'm going to assume you know Bayes in its entirety now. This is about it. Now there's phenomena that we need to talk about, mathematical derivations, and then, of course, all the fancy stuff that people are doing nowadays. So computational stuff. Any questions? We know how to get posteriors. We know how to get predictive distributions. So if you can't do the integral, we know how to use our computers. And if you don't know how to draw from the distributions perfectly, I'm going to show you tricks for that in the future when I teach you at CMC. Any questions moving forward? Okay, that's it for now. I'll see you guys next time, and we're going to switch gears. I think we might do some easy preliminary stuff. I'll give you some definitions, and then we'll start moving into something novel. Thanks, guys.